Hello everyone, welcome to my 11th live presentation in CS internship. My name is Maliheh Sefat and today I talk about neural nets with TensorFlow and I show you sequential, functional and subclassing APIs. So what is Tensor and TensorFlow? TensorFlow is a framework that builds and manipulates tensors to perform machine learning and deep learning computations. In TensorFlow, almost every object being data, parameter, operations is represented as a tensor. In calculus and linear algebra, tensors are used to represent multidimensional data and relationships. In TensorFlow, a tensor is a core data structure that can represent a scalar, vector, matrix, or n-dimensional array. It's essentially a container for data with known attributes such as shape, rank, data type, and supports a wide range of operations and functionalities. Here, if we have a tensor of just one element, one scalar, it would be rank 0, and the shape shows like empty parentheses, exactly as NumPy. And then if we have vector as a tensor, the tensor is ranked 1 and it shows with one number for the number of elements, the shape. The shape of a tensor built from a matrix is shown by 2 dimension. This is a 2-dimension matrix, so the tensor is rank 2, and then we have higher ranks and higher shapes. So we import the NumPy and TensorFlow as TF. TensorFlow includes versatile libraries such as Keras. So we import from TensorFlow, import Keras, and from Keras we import layers. This is called deep importing, and it's not recommended, but it's okay for layers. After that, we set the precision of floating numbers to be 3 and set the seeds and import the other libraries that we need. And now we make tensors from NumPy arrays. If we have a NumPy array S with just one element with value 1, we can convert it to tensor with convert to tensor method. tf.convert to tensor makes a tensor of this. And you can see that it shows TensorFlow tensor, shape is empty parentheses, data type is integer 64, and NumPy value is 1. And then we can have a list of elements in the NumPy array, and then we can have one row of elements. This is one row, this is one list. So the shape shows like this. The first one, just one element. The second one is 2-dimensional. So we have 2 dimensions. And the tensor shows like this. This time the data type is integer 64. We can have immutable tensors with constant method. And we can also pass strings to that tensors. So the NumPy value shows as byte object, and data type of tensor is object. Of course, you can have the length of those with tf.string.length. There are several, many actually, functionalities and attributes of tensors. TensorFlow is better for neural nets than scikit-learn. Scikit-learn is great for simpler models such as decision trees and logistic regression, but it's not optimized for deep learning. On the other hand, TensorFlow is designed for deep learning. It's specifically built for neural nets and large-scale machine learning. It supports GPU acceleration and it can support TPU. TPU is tensor processing unit, which is built for tensor calculations. And also TensorFlow offers flexible architectures. We can build custom models. And then we have the Keras, which is a Python-only API for working with TensorFlow. In TensorFlow Keras, there are 3 primary paradigms for constructing neural networks, neural nets. Keras Sequential API, Functional API, and Subclassing API. Sequential is ideal for straightforward models with a single input, single output point, and it's very good for building a quick model. It's beginner friendly. It works like this. We define the model as tf.keras.sequential function, and we pass the layers inside a list to that sequential. So we have a list of layers. Here we have layers.input, which is the input layer. We pass it the shape of the input if it was two elements, two features only. And then we can have different layers. Here I have a dense layer with 3 units and activation Relu, and then another dense layer with 1 unit for the output and activation sigmoid for binary output. With the summary function, summary method, we can get and see the architecture of our model. Here shows 3 units in dense layer 0 and 1 unit in the other dense layer. We have 9 parameters in the first because 3 units multiplied by 2 inputs is 6 plus the 3 biases. So we have 9 parameters. In total, we have 13 parameters. Another syntax for building the same sequential model is to have the Keras sequential, but it's empty. We don't pass it anything. Instead, we add the layers with the add method one by one. We add an input layer, add the dense layers, add the final layer, and when we get the summary, you can see that we still have the same 13 trainable parameters. Another syntax for the same sequential architecture is to have the layer separated, the units separated from the activations. Why? Because this way we can insert other layers in between weighted sum and then the activation. For example, here I inserted a dropout layer and a batch normalization layer if we haven't done the normalization in the pre-processing. And when we get the summary to see the architecture, now we have more parameters, but some of them are not trainable parameters. These 4 parameters for the activation, for connecting this activation is not trainable. While we are on the subject of syntaxes, we can also pass the input inside the layer, but it's not preferred. The best practice now is to have a layer, a separate layer for input. It says a warning that you shouldn't use input shape as a keyword argument. Another best practice is to use keyword argument for units, not the positional syntax. Although at the end of the day, the best practice is consistency. You should be consistent all over your project and program. Here is different, shows the different syntaxes for passing the activation. We've seen so far how we pass the activation as a string with a string identifier, for example, a string Relu, a string sigmoid. Another way is to pass the activation as an NN module of the TensorFlow function, the function of NN module, tf.nn.relu. Another way is to have the Keras activation, keras.activation.relu. So to work with our models, we define an XOR classification problem. The exclusive OR problem is defined like this. We have numbers with we have points with 2 features, x1 and x2, but they have different signs. If the signs of 2 points if the signs of the features are the same, the answer to the XOR problem is 1. If they are not the same, they differ, one is negative, one is positive, the answer is 0. This is the definition of XOR, and this is one data set of XOR. This shows XOR. So we construct a sequential model. We have 4 dense layers. 3 of them are hidden layers with 4 units. The last one is 1 unit because our problem definition requires 1 input y. And again, our problem definition requires the input shape to be to show 2 features, a vector with 2 features. So each model is specifically for that problem because the input shape and output shape and what we use as activation is defined by the problem. Also, we can name the we can name the layers if we want. If we don't name them, it it automatically chooses a name, and the name is because of the order. As I run these cells, this one get the name dense42, but these are the names that I put here. So we have 57 trainable parameters here. If we don't give the model an input layer and input shape, if for some reason we don't pass the input shape, we can do the late variable creation with build method, model.build, and we pass the input shape here. This is called late variable creation. So after that, we need to compile our model and prepare our model for training. We define the hyperparameters, which is the optimizer, the loss function, the metrics that we want to measure. Optimizer controls how the model learns from the data, for example, with the gradient descent calculation. And loss function measures how far the model's predictions are from the ground truth. Loss function shows the cost, the error. And metrics determines what performance indicator to calculate during the validation evaluation. So here we compile the model with optimizer, stochastic gradient descent, and loss function binary cross entropy because our data is binary, and metrics is binary accuracy, again because our data is binary. I trained the model with the fit here, pass the X train and Y train, pass the validation sets. I set the epochs to be 100. I want 100 epochs of training. I set the batch size to 3 just because. And this verbose 0 turns off the training log display. I show you what is that. But we can collect the training log inside a variable. We call it hist. Typically, we call it hist or history, and get the history of the hits. This history is a dictionary that the keys are loss and optimizer that we defined. The optimizer here, the loss and metrics that we defined. So with that history log, we can plot the performance of learning curves. Here's the learning curve for accuracy and loss. We can see that we reached accuracy of training 96%, and the accuracy of validation is 92. Let's see what this model do on unseen data, test data. We build the test data set of 60 points, and you see that we reached 93% accuracy on the test. It's not bad. So the second API is functional API. In functional API of Keras, each layer is defined as a function, and then the model is defined as a function. Here we have the function input for the first layer and we collect the inputs. Then we pass these inputs to the next layer. We define the next layer, name it h1. This whole line here works as a function, and we pass the inputs to it. Then we pass the results to the next layer. Then we pass those results to the next layer. And for outputs, we pass the result of the hidden layers here to the function of outputs. And then we build the model with tf.keras model function and pass the inputs and the outputs to it, just the input and output, not the hidden layers. When we get the summary, you see that we have the same 57 trainable parameters. Another API is subclassing API. Here, we subclass the model from that tf.keras model. Here, we can do many creative things and build custom layers and so on. Here, in the subclassing API, each layer is defined as attributes of the class with the self-hidden, self-output, you see? And to activate them, we need to call them. We pass the inputs to the call function, and we do the same functional things, pass the inputs to the first layer, then pass the results to the next layer, and then return the self.outputs layer results. Then we need to instantiate the model with calling it. And here, the model shows, when we get the summary, the model shows that it's unbuilt. There's no parameter, zero parameter. Even if we do the late variable creation with the build, but it's still, we only get a warning that says don't pass input shape like this. This is not good. But it's not built yet. When it's built, when we pass the first input, when the model sees the first input, it is implicitly built. So when we pass just one point and go one in forward pass, now our model is built and shows the 57 parameters. So let's skip the comparisons. I put it in GitHub and you can see that. In this step, we didn't have a project, so I defined a project for myself. For this project, I used the MNIST Fashion dataset, which is built in the datasets of Keras. Calling it and loading it is very easy with the load data function. And you see that we have 60,000 images of clothing and 10,000 labels. Those labels are here. These are the label images. I don't know what happened. So it shows a preview of the image, and when we click on it, it shows the numbers. And then these are the rows. The numbers, the images are 28 by 28 matrices with numbers between 0 and 255. I don't know what happened here. So, and these are some of the labels. The labels correspond to these names. The label 0 is t-shirt. The label 1 is trouser. And the label 9 is ankle boots. And to show you some of the images. They are like this: grayscale, 28 by 28 items of clothing in 10 different classes. Now we do normalization. It's very easy in this case. Just divide by 255, and then we split a validation set, 12,000 validation images, and we build a simple sequential model with 128 hidden units here. This flattened layer, it's a layer, and it flattens the shape of 28 by 28 into a 784 by 1 vector or matrix. Okay, then we compile the model, this time with the optimizer Adam. Loss function would be sparse categorical cross entropy, which is good for multi-class classification. And the matrix is accuracy, and we train the model. Here we train it 5 epochs, batch size I decided to be 16. The default is 32, so batch size 16 trains the model slower and pass the validation sets to see what happens. Here is the log that I told you about. We didn't suppress the logs here with verbose 0. And we reach validation loss of 0.33. Here we evaluate our model on the test data, and you can see that we reached 86% accuracy for the test data. When we get the prediction with the predict method, the predictions are probabilities between 0 and 9, or between 0 and 1. And you see that it's 90% probable to be the first image here to be ankle boot, which is accurate. The first image is ankle boot. So we can do another plotting to show you where the model was wrong. Here, for this image, the true label was caught, but the model predicted pullover, which is understandable. And this one was caught. The model predicted pullover again. And then we access the log history and plot the training curves or learning curves. You see that we have a slight overfitting here. The accuracy of training is more than accuracy of validation, and the loss of training is less than the loss of validation. To find a better model, I tested several other changes in the model. One is to test wider or deeper architectures. Here, if we add the number of layers, that would be a deeper model. And if we add the number of neurons in each layer, this is a wider model. The blue dots are inputs, the red dots are outputs, and the greens are hidden layers. Here we have a deeper layer. It goes deep into the layers. Here we have a wider model. If we have a wider model, we construct the same model, but only with 1024 units in the hidden layer. Actually, it doesn't help much, and we don't get a better accuracy and loss. And it shows that the model tends to go even more overfitting, even more overfitting. If we add the complexity by adding to the layers, we have the same number of units here, but the layers are more. We have 8 layers of 128 neurons. And we do the same with the same optimizer, loss, and metrics. You see here the accuracy is better, slightly better, but the loss is not better. And the overfitting is a little better. What if we do more epochs? If we want to do more epochs, we have to tell our model to stop somewhere. It cannot go on and on. We need to stop training after we don't see any meaningful improvement because training is expensive. So we use early stopping from the callbacks of Keras to stop the model when it doesn't see any improvement. Here we have these arguments. We monitor the val loss and we consider a 0.002 the mean delta as the improvement, the minimum amount of change that we count as improvement. And we wait for 4 consecutive um, epochs to see any improvement. The instruction is that if there hasn't been at least an improvement of 2,000 in the validation loss over the previous 4 epochs, then stop the training and keep the best model you found. Here, report best weights true. It keeps the best model, rolls back the model to that best set of parameters. Now, we use this early stopping on the first simple model, one hidden layer with 128 neurons. And this time we give it 50 epochs opportunities. Okay. But we use the early stopping to not waste computational expenses. Here you can see the log. The log goes like this. At first, the loss is 0.39. Then it's in the next epoch, it's 35. Is it better? Yes. So this set of parameters are kept as the best. After that is 32. So this one is the best so far. 33. This one is better. 33, 330. Okay. We set the precision, the mean delta, to 2000s. So this one is 4000s better. This one is the best. Then this one. But the next epoch shows not an improvement. And then the next. So this is not better. So this one is better than 328. 322 is better. So this one is the best so far. These sets are kept. Then the model sees a downgrade. The loss goes up, validation loss goes up. 1, 2, 3, 4 epochs, the model waits, and it doesn't see any improvement, so it stops at epoch 12 and gives us the evaluation of accuracy of the test set. This experiment shows that when our model tends to overfit, it doesn't help to add more epochs. It doesn't help to train for more time. It just increases the overfitting. To get a better model, I tried different approaches. One is to use dropout regularization. Dropout regularization goes like this. For some training epochs, for some training forward pass, we want to shut off some of the neurons. Those neurons, these purple neurons here, in that forward pass, don't receive any update in the weights. For example, here in this layer, we chose to shut off 50% of the neurons randomly. This randomness adds an element of stochasticity or flexibility or complexity to our model. So we with the same structure and with the same input data, we have a more complex model. And this regularization helps the model to not overfit, to not memorize the data. Another thing that I tried was to use LeakyRelu instead of Relu. LeakyRelu allows some non-zero gradient, some small non-zero gradient when the input is negative. Also, we didn't have the negative inputs in our images, but the output of hidden layers could be negative. Okay, and we don't want to face doing-ReLU problem. So we want the model to be able to pass just a little small negative values with this slope attribute here, this slope attribute of the LeakyRelu. Here, I changed the model. I changed the earlier stopping to count 1000 as improvement. 1000 is acceptable as improvement, and it also waits for 10 epochs to see any improvement. I also separated the functions, the activation functions, because LeakyRelu cannot be passed as strings to the dense layers. It has to be a separate layer. We have separate layers of LeakyRelu, and then we have the dropout layers. I want 20% of the neurons in each layer to not receive any update randomly. And then the rest are the same. We use optimizer Adam, loss, sparse categorical cross entropy, and matrix accuracy. And this is the log. It goes on until epoch 45, sorry. And here, this one, 0.295 was the best loss. And after that, no, 0.294 was the best loss. And it counted 10 epochs, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 epochs to see any better improvement, and it didn't see, so it stopped at the 45 epoch. And here you see that we have a slightly better model. The loss on the test set is 31, and the accuracy is 88% accuracy. And here's the confusion matrix for the best model that we have so far. You see that mostly pullovers were confused with coats, and shirts were confused with t-shirts. And this concludes step 11. Thank you very much for watching my presentation.